In the previous video, we looked at Carey's example of a t-test comparing male, female falcon wing lengths, assuming unequal variances. And now we're just going to repeat that using an alternative flowchart and model. And as I said earlier, one of the big challenges in doing this kind of thing, doing this data analysis, is to get proper alignment in our minds of the data, the flowchart, and the code for the model. And in this case, I'm going to begin with data preparation. So we're going to begin with this data frame, and then here we've got a bunch of code that involves some modifications. And the first thing I'm going to do is I'm going to create this object called design, which is going to be a vector consisting of the number 1 repeated 60 times, followed by the number 0 repeated 40 times. So there's design with 60 values of 1, followed by 40 values of 0. And then I'm going to create another variable called sex. I'm going to use the if-else function. And the way the if-else function works, it begins with this thing here, which is, I can refer to that as a truth condition. And it's going to be either true or false. And if it's true, then sex will equal this first number 1. And if the truth condition is false, then sex will equal this value of 2. So essentially what happens is, if this is a value of design, for the first 60 cases in which design is equal to 1, then the value of sex is going to equal to 1. However, if this truth condition design equals 1 is false, like it would be here, then the value of sex is going to equal the value of 2 that you see here. So now we've created this new value of sex, which is going to be 1 for the males, and we're going to see 40 for the females. And then I'm going to create another value y, which is going to be a vector. And I probably didn't really need to do this. This probably would have been adequate right there, that says, okay, that this y value is simply going to be whatever these numbers are here. Now, previously, I defined in other videos n total and n sex using the len function. Here I specify them directly by saying that the total number of observations was 100 and the number of different sexes was 2. So at this point, I've got data file, which consists of a list, which has these 1, 2, 3, 4, 5 components. And here you can see them here. That essentially consist of design, sex, y, together with n total and n sex. So here is our flowchart. So we're going to begin at the bottom, as we often do, typically do, with the likelihood function. So there's our likelihood function. And what we're saying is these values of y are going to arise from a normal distribution that has a mean mu I and a precision that's written like this. Now, let's begin first with mu I. We're going to define mu I. There's our equal sign here. Mu I is going to be this guy. So effectively, we could erase mu I and just replace it with this guy here. Which brings up the obvious question of, what the heck is this guy here? And what I meant to do is show what it means right here, is that I take the value of B0, and I add to it B1 multiplied by design, and here's our value of designs, a series of ones and zeros. So if I start off with B1 and add to it B1 by design, since design right here is 1, I get B0 plus, and that should be a B1, and that should be a B1. Thank you very much for Excel's auto adjust. And that should be a B0, and that should be a B0, and that should be a B0. Thank you again, Excel. So what I have here are B0 plus B1s, and here I'm going to have B0s. So my 60 males and my 40 females, the value of B0 plus B1 multiplied by design is either going to be this or it's going to be that. Okay, so that's a start on our likelihood function. Now we've got a pretty good idea what the mean is going to be. How about the precision? Well, again, we've got this double square bracket nested indexing. So let's think about how that would work. And let's do some examples. Let's consider TAW, sex, 1. What would that be equal to? Well, I've shown here that all these values of y, they're going to be implicitly indexed by row number. So if we've got TAW sex 1, if we've got TAW sex 1, when I is equal to 1, sex is equal to 1. So this is going to be TAW 1. And what happens if I have TAW sex 99? Okay, when I is equal to 99, what is sex equal to? Sex is equal to 2. So I've got TAW 2. So TAW 1 is precision for the males. TAW 2 is precision for the females. So that is our likelihood function. So after our likelihood function, what we need are our priors. And I've specified the priors for B0 and B1 as relatively flat priors. Now, let's think again what's happening here. We've said that these values of y are going to be drawn from a normal distribution with this mean, but this mean is going to be equal to this thing here. This thing here. So essentially what we've done is we've reparameterized our normal distribution. So it's now got as its parameters what? Well, design is fixed. So it's got these two new parameters, B0 and B1, that we are trying to estimate. So we need priors for B0 and B1, and we're going to specify relatively flat priors for them. Then we come over to the priors for TAW, and again we go through that two-step process where we assume that the standard deviation, sigma, is derived from a relatively flat uniform distribution, and then we obtain our value of TAW as being the reciprocal of the standard deviation squared. So that's our flowchart. But again, remember, if we come back here, there's one final thing to go over, and that is, again as a reminder, we've reparameterized our normal distribution, so it's now got parameters B0 and B1, but what we're interested in are the wing lengths of male and female falcons. But if you come back here, you can see that for the males, their wing length is determined by B0 plus B1. For females, it's determined by B0. So these are derived quantities that says that for the female, their wing length is going to be B0, and for the males, it's going to be B0 plus B1. And so with all that underway, really all we got to do is convert the flow chart into the model statement. So we begin with our likelihood function. There's this open and closed parenthesis. And what we've got in these two lines is this bit here. So the yi's come from a normal distribution with mu I and toss xi. That's this bit. And then we say, okay, this mu I here is equal to that thing there. So that's our likelihood function. And then we do our priors. Excuse me. Now, remember what we have to do. We need priors for tau1 and tau2. And I could have said, I could have specified tau1 prior and tau2 prior, but I decided to do that specification instead of doing it directly, do it in a loop. So I loop from sex 1 to 2. And so I just say, again, we're going to use this two-stage process where the standard deviation is derived from a uniform distribution, and then we obtain tau as being the reciprocal of the standard deviation squared of the variance. And so we loop through those two sexes, and so we get tau1 and tau2 being derived ultimately from sigmas that come from, excuse me, uniform. So those, what I just went over, are those priors there. And what we have here are the priors for B0 and B1. Priors for B0 and B1 are shown here from flat normal distributions. And then finally, we get our derived variables. It says, okay, the females are equal to B0 and the males are equal to B0 plus B1.